Yeah, thank you for coming to my talk, everyone. So today I'm going to give a talk giving a fairly high-level overview of how we can use some tools from quantum information theory to build toy models of the ADS-CFT correspondence, and then explain kind of why these toy models are useful and yeah, how we can use them both to kind of get you insight into ADS-CFT and also to get some new results in quantum information theory. So this is joint work with Harriet, Toby, and Patrick, who are all here this week, and David Garcia in Madrid. Okay, so first of all, what is ADS-CFT? So we have had a couple of talks on this morning, but just so we're all on the same page. ADS-CFT is a kind of manifestation of the holographic principle in quantum gravity, where the holographic principle says that quantum gravity in d+1 dimensional space-time is equivalent to a many-body system defined on its boundary. And ADS-CFT is kind of the key example of the holographic principle, where in this kind of acronym, ADS refers to anti-de Sitter space, which is kind of a space-time that is maximally symmetric and has constant negative curvature. So throughout this talk, we're mostly going to be thinking about just kind of fixed time slices of ADS, and for that we can just view it as being kind of a hyperbolic plane. And the CFT corresponds to a conformal field theory. So the idea is that some quantum gravitational theory living in ADS space is kind of fully captured by a conformal field theory living on the boundary of that space. So all the information about quantum gravity, you can kind of forget about gravity. You don't have to worry about that at all. Just study kind of a standard conformal field theory. And if this duality is true, that's all you should need to study to understand quantum gravity. Obviously, it's not that easy. If it was, we'd have a full theory of quantum gravity already. And the issue is there's no kind of complete mathematical description of this correspondence. And that's led to interest in kind of trying to build toy models of the correspondence to gain some intuition for what's happening and to try and probe features of the duality. And it turns out that kind of techniques from quantum information theory can be really useful in studying the correspondence and in building these toy models. So when I say a toy model of ADS-CFT, what do we want from a toy model? What features should some model have to be a good toy model of ADS-CFT? Well, first of all, this duality is expected to be an error-correcting code. And this kind of relation to quantum error correction is really kind of, I think, one of the main reasons why people started looking at using techniques from quantum information theory to study the duality. So what do I mean when I say ADS-CFT is an error-correcting code? As I said, ADS-CFT is this duality between a bulk gravitational theory and a non-gravitational theory living on the boundary. And the way this kind of duality works is that if you have some kind of bulk operator or bulk state living in some part of the bulk, the idea is that you can kind of recreate that operator or state on the boundary on a boundary region if the operator lives in what's known as the entanglement wedge of that boundary region. Where for this talk, we can just think of the entanglement wedge of a boundary region as being captured by the kind of the area contained in the geodesic that goes through the bulk. So if we could take some particular boundary region, draw a geodesic through the bulk to the other end of the boundary region, all the kind of area captured between the boundary and that geodesic, that's what we're going to call the entanglement wedge of that boundary region. And as you can see here, this bulk operator is living in the entanglement wedge of this boundary region. And that means that we can recreate this bulk operator purely looking at this boundary region. So that means we can erase a kind of fairly large portion of the boundary without losing any information about operators living in this portion of the bulk. So in that sense, ADS-CFT is kind of like an erasure error correcting code. And obviously this kind of bulk operator doesn't live purely on this boundary region. There are many other boundary regions which have this bulk operator in its entanglement wedge. So we have kind of redundant encoding of operators. Okay, another reason why kind of people think that quantum information theory is related to ADS-CFT is because in ADS-CFT, there's a relationship between entanglement and geometry. And this relationship is captured by what's known as the Ruta-Kanagi formula. And this formula says that the entanglement entropy of a state living on a particular boundary region is proportional to the kind of to the length of this geodesic here, where again this geodesic goes through the bulk and kind of bounds this boundary region. Okay, So these are kind of two places where quantum information theory and ADS-CFT intersect. And this is kind of some of the reason why people think, why people have used quantum information theory to study the ADS-CFT correspondence. So any toy model of ADS-CFT should kind of capture these properties. We also want our toy model of ADS-CFT to be a dynamical toy model. So we want there to be Hamiltonians there controlling the dynamics. And we want the boundary Hamiltonian to be geometrically local. And there's a couple of reasons we want this. First of all, in conformal field theories, the Hamiltonian for a conformal field theory is local. And secondly, if you have some kind of, maybe a bit more philosophically, if you have some kind of crazy global Hamiltonian living on the boundary of some kind of hyperbolic space, there's not really a real sense in which that boundary Hamiltonian is living on the boundary anymore. You know, if you don't have a geometrically local boundary Hamiltonian here, what do we mean by a boundary? You know, you can, if the interaction graph isn't actually living in this dimension, is it really a holographic theory? So that's why we want this boundary Hamiltonian to be geometrically local. We don't necessarily need the boundary Hamiltonian to be geometrically local for completely arbitrary bulk Hamiltonians, but if the bulk Hamiltonian is either local or quasi-local, then we would expect the boundary Hamiltonian to also be local. Okay, and I mean, there are many other features we might want a toy model of ADS-CFT to have. I'm concentrating on these three because we do have a toy model that captures these three. But towards the end of the talk, I will touch on some other properties we might want that we don't yet have. Okay, so in the rest of the talk, I'm going to start off by giving an overview of some kind of earlier work on holographic quantum error correcting codes. And I'm going to talk about Hamiltonian simulation techniques. And these two kind of techniques together, holographic error correcting codes and Hamiltonian simulation, come together in our construction to give a toy model of ADS-CFT that has the three properties I've said that we want. So once I've explained our construction, I'm then going to discuss an application of the construction to position-based cryptography, where we actually use one of these toy models of ADS-CFT to get a new result in quantum information theory. And I'll finish up with discussing some open questions. Okay, so first of all, holographic quantum error correcting codes. Okay, so as I've said, in this talk we're going to be focused on constant time slices of ADS. So for now we can kind of forget about, well, put ADS to one side and just think about the hyperbolic plane. And we're going to construct a toy model of ADS-CFT by tessellating the hyperbolic plane. Here we've got it tessellated by pentagons, but you know, pick your favorite tessellation of the hyperbolic plane. And then what we're going to do is we're going to put a perfect tensor in each cell of this tessellation. Where a perfect tensor here, there's kind of a few different equivalent definitions of a perfect tensor. But essentially it's a tensor that's an isometry across any bipartition. Equivalently, it's a tensor that describes a maximally entangled state, or one kind of thing that will be important for us is it's a tensor that describes the encoding isometry for a good quantum error correcting code. Whereby a good quantum error correcting code, I mean an error correcting code that saturates the singleton bound. So if you don't know what that is, don't worry. It's just a good quantum error correcting code. Okay, so I said we put a perfect tensor in every cell of the tessellation. And these perfect tensors are kind of depicted by these grey circles. The blue dot that you can see in each grey circle, that's kind of a dangling leg of the perfect tensor. So that's a leg of the tensor that isn't contracted with anything else. The other kind of 5 legs of the perfect tensor, you can see, these are contracted with the tensors that are placed in neighbouring cells of the tessellation. So this is what we have here is a 6-leg perfect tensor, where for all of the bulk tensors, 5 of those legs are contracted. Then we're going to cut off this tessellation at some finite radius. So this tessellation of hyperbolic space is in reality infinite, but in order to get a solvable toy model, we're not going to kind of fill this tessellation with tensors out to infinity. Instead, we're going to cut it off at some finite radius. And you can see when we cut it off at some finite radius, there are these kind of red legs of the tensor that aren't contracted with anything. And these are going to be our boundary degrees of freedom. So because of the properties of perfect tensors, you can show that this tensor network gives you an isometry from the bulk degrees of freedom to the boundary degrees of freedom. That's fairly straightforward to show. You can kind of see it just by remembering that each of these tensors is itself isometry. Okay, so we have an isometry from bulk to boundary. That's a bulk boundary correspondence. We've got, some flavor of ADS-CFT here. But what other features of the duality do we have from this toy model? So it turns out the error-correcting properties of ADS-CFT are well captured by this model. And that's because, as I said, these perfect tensors aren't just isometries. They're encoding isometries for error-correcting codes. So that means if we have some information on this central bulk Q bit here, that we want to kind of push out to the boundary, we don't have to push that information through all 5 legs of the tensor. We can just push it through any 3 legs. And because of the error correction properties of this tensor, that retains all the information of this bulk degree of freedom. And we can kind of keep doing that as we go out through the tensor network. And in the end, we'll find that there's some finite portion of the boundary which encodes all the information about the central bulk tensor. And it turns out this finite portion of the boundary is sort of what you'd expect from ADS-CFT. You can kind of view it as you can recreate a bulk information on the boundary if it lives in the entanglement wedge of the boundary region. Okay, so that's one of the properties we wanted for ADS-CFT. We've got it in this toy model. And this toy model sort of captures the expected entanglement properties. It doesn't exactly obey the Rutaka-Nagy formula, but for certain simple bulk regions, you can kind of say that the entanglement of that boundary state is upper bounded by the Rutaka-Nagy formula. So it's not gone all the way, but it's a nice toy model that gets some of the features we want. Okay, so how can we do better? Well, we can go one step better by replacing perfect tensors with random tensors. So here again, we don't necessarily need a tessellation of hyperbolic space in this case. We could have some arbitrary random graph with kind of a negative sense of negative curvature. And in every vertex of that graph, we're going to place a random tensor. And again, we'll contract up tensors through edges in the graph, and we'll leave dangling bulk legs as our bulk degrees of freedom. Okay, and when we do this, what does it gain us? Well, it turns out if we replace perfect tensors with random tensors, we get even better error correction properties. So I said that the previous tensor network model gives us some nice error correction properties of ADS-CFT, but there's some particular properties known as complementary recovery, which we don't quite get in the previous toy models, and we get closer to it in this toy model. I think the more kind of exciting benefit of this toy model is that we really do now capture the entanglement features of ADS-CFT. And it's kind of very beautiful the way that they show that in this paper. They show that the second Renyi entropy of these random tensor networks can be mapped to the Ising model. And it turns out that in order to calculate the entropy of kind of arbitrary boundary regions, you need to look at kind of transition points in the Ising model, and it will be kind of the lengths of these boundaries that give you the entanglement of your boundary region. And it turns out the lengths of these kind of regions are exactly the lengths of these geodesics. So you really get exactly the entanglement properties of ADS-CFT that you want from this toy model. She said this doesn't work for kind of low-dimensional random tensors. You really need to have high-dimensional random tensors for this to work. But we're modeling ADS-CFT. In ADS-CFT, probably you want infinite dimension. So I think large local dimension is fine. Okay, so this gets us a step further to a toy model. What do boundary Hamiltonians look like in these toy models, though? So if we start with some local bulk Hamiltonian, so we're going to just, for argument's sake, start with a 2 local bulk Hamiltonian, and we look at what this looks like on the boundary, what do we get? Well, we can do this by taking the bulk terms in our Hamiltonian and pushing them out to the boundary. And when we do that, because of the way that the tensor network spreads information through the bulk, we end up with a boundary Hamiltonian term that acts over a very large portion of the boundary. So in particular, bulk Hamiltonian terms from the center of the bulk will map to boundary terms that act on an order 1 portion of the boundary, which is not what we want for ADS-CFT. Okay, so how are we going to fix this up? We're going to use techniques from the Hamiltonian simulation literature to kind of fix up these toy models. So first of all, what do we mean by Hamiltonian simulation? Well, in perfect Hamiltonian simulation, the idea is that you take some Hamiltonian with interesting physics that is too complicated to study, And you use some encoding map to map this interesting physics into the low energy subspace of a Hamiltonian which is simpler in some way. And this encoding map, throughout this talk, we can just think of it as being an isometry. There are some slightly more general things that are allowed, but for this talk, this encoding map will always just be an isometry. And we say that this mapping is a perfect simulation if the low energy part of this Hamiltonian is exactly equal in operator norm to this encoded Hamiltonian. And these things are equal in operator norms, so in particular that means the entire spectrum is preserved, all measurement outcomes, thermal properties, time dynamics, all the information about this interesting Hamiltonian is captured by this simpler Hamiltonian. The reason this is interesting is because these two Hamiltonians can have different interaction graphs. Okay, so this is perfect Hamiltonian simulation, but perfection is a high bar. So what about if we loosen that a little bit and say let's look at approximate Hamiltonian simulation? So the kind of full definition of approximate Hamiltonian simulation is a little bit involved, so I'm not going to go through it here. Instead, I'm going to kind of give a slightly high-level overview of what we mean by it, which will hopefully be enough for people to understand the rest of the talk. So we're going to say that some Hamiltonian H prime is a delta epsilon eta simulation of H if below delta H prime approximately simulates H. So delta here is our energy cutoff again. So the interesting Hamiltonian H is encoded into the spectrum of H prime below delta. Above delta, the spectrum of H prime might be doing crazy things. We don't care about that. We're just interested in energies below delta. And okay, what are these epsilon and eta parameters doing here? Broadly speaking, we can think about epsilon as being the error in the eigenvalues of the simulation. And then eta, we can think of it as being the error in the eigenvectors of the simulation. This is a little bit hand-wavy. There is a more mathematically rigorous definition, but for our purposes, we can just think of these as being two errors that do affect the simulation for approximate simulations and affect different parts of the simulation. Okay, and if we start off by encoding our Hamiltonian H into this simulated Hamiltonian H prime and let it time evolve, when we start off, we've got kind of zero error in our state, and we're going to let it time evolve under this approximately right Hamiltonian. We're going to find that errors in the simulation grow like this. So you can see that the epsilon error is kind of more important as time goes on. It grows with t, whereas our eta error here is not so important. It just is a constant. And typically for approximate simulation techniques, you can make these epsilon and eta parameters as small as you want at the cost of increasing the norm of your simulator Hamiltonian. Okay, so this is a fairly abstract definition. Why don't we look at some examples to try and make this a bit more concrete? So in particular, the examples we're going to look at are perturbation gadgets. And the idea of perturbation gadgets is that we have some complicated interaction graph. We want to simulate it with a more simple one, and we do that by perturbation theory. So in particular, we're going to start off with a subdivision gadget. The idea in the subdivision gadget is that we have some k-local Hamiltonian term where k is large. And we want to break this down into a Hamiltonian term acting on a smaller number of qubits. And we do that by adding a mediator qubit here. You can see this mediator qubit has been added between the two graphs. And the idea is that we apply a very heavily weighted term to this mediator qubit, so that in the low energy subspace of this Hamiltonian below, this mediator qubit is going to be living in a one-dimensional subspace. And then the idea is that then in this one, by forcing this mediator qubit to stay in a one-dimensional subspace, we can then use it to mediate an interaction between these two groups of qubits that aren't actually directly interacting with each other. We can do a similar thing if we have a crossing in our interaction graph. We want to get rid of that crossing in order to have a planar graph. And again, we do that by introducing a mediator qubit. And again, we have some heavily weighted projector that forces this mediator qubit to live in a one-dimensional subspace. And then by adding these kind of additional interactions, what we do is we end up mediating interactions between these qubits, even though they aren't directly interacting with each other anymore. And similarly, we have a fork gadget, which we can use to reduce the degree of any vertex in the interaction graph. And again, we do that at the cost of introducing one additional mediator qubit and again, having some heavily weighted projector. Okay, so as I've said, in all of these perturbation gadgets, the mediator qubit is acted on by some heavily weighted projector. We should also note that each perturbation gadget from the previous page acts on a single Pauli term. So if we have some Hamiltonian term that's a sum of Pauli terms, we're going to need to treat each of those Pauli separately. Okay.
Sorry, how do those weights scale, and do you to get the gadgets to work?
You don't need to be very precise about them to get the gadgets to work, but basically, the higher you have the weight, the smaller the errors. So if you don't care particularly about the error, you're only going to be doing the simulation for a very short time. You don't need that J to be this J to be that large. But if you want the simulation to be valid for long times and the epsilon error is going to grow with T, this J will have to be very large in order to keep the error manageable. So later in the talk, we will have some examples of some of the scalings. Okay, so using these kind of gadgets, you can provably show that you can simulate any Hamiltonian at all via two local Hamiltonian on a lattice that has a lot of symmetry. And the costs you pay for this are increase in the norm of the Hamiltonian and additional degrees of freedom. So these mediator qubits are additional degrees of freedom we have to cope with. Okay, so that probably gives some kind of insight to how our construction is going to work. We have these nice toy models of ADS-CFT, which give non-local Hamiltonians on the boundary, and we have a way to simulate non-local Hamiltonians with local Hamiltonians. So we're kind of done, right? We can take a holographic quantum error correcting code constructed from Haar random tensors. So this code has all the properties I mentioned before of these random tensor network models. It has the error correcting properties, and it has the entanglement properties. And then we can use Hamiltonian, but it has a very non-local boundary Hamiltonian. But then we can use Hamiltonian simulation techniques to simulate this non-local boundary Hamiltonian with a local Hamiltonian. And this does work. You can do this. But what you find if you do this is that the local Hamiltonian on the boundary is acting on exponentially many qubits, or qudits, because this is high dimensional, compared to the original boundary Hamiltonian. So this is kind of unsatisfying.
Where is the exponential coming from?
So yeah, I'll get there. So the exponential is because, so k local terms deep in the bulk map to terms in the boundary acting on an order n portion of the boundary. But these terms have Pauli rank exponential in n. So for every term in the Pauli decomposition, you have to do another gadget, and that gives you an exponential blow up in the number of spins on the boundary. And this is kind of unsatisfying because because this isn't really a boundary anymore. If we kind of want to say that space-time, there's a kind of fixed density of information we expect in a space-time region. We don't expect kind of the conformal field theory to be much, much denser than the ADS space. Then in order to satisfy that, we're going to have this boundary pushed out from the actual boundary of the toy model. And we end up with something that morally doesn't really feel like a boundary anymore. If you take these distances, you've got a lot of empty space to go through before you actually get to the ADS space that we're interested in. So this sort of works, but not in a particularly satisfying way. And as we were saying, the reason we get this exponential blow up is because even though we started with terms of Pauli rank k for some fixed k, when we push these terms through the tensor network, we end up with Pauli rank exponential in n, which causes this kind of which means we have to do exponentially many gadgets. Each gadget only requires a log n rounds of perturbation theory, because we can kind of do these things in parallel. So the number of rounds of perturbation theory and the kind of interaction strength doesn't blow up too much, but the degrees of freedom really blows up a lot. Okay, so how can we tackle that? So the key idea is to use random stabilizer tensors instead of Haar random tensors. And as I'm sure most of you know, random stabilizer tensors are obtained by applying a random Clifford to a reference state. So essentially, when I say you can think of a random stabilizer tensor as being like a random stabilizer state, as the tensor that describes a random stabilizer state. And we know that random Cliffords form unitary 2 designs. So that means that any results from the random tensor network paper that only use second-order moments of the random tensors can just be ported over for free to a construction that uses random stabilizer tensors instead. And in fact, we can even use some other additional properties of random stabilizer tensors to go a little bit further. So random tensors are approximately perfect with high probability. But it turns out random stabilizer tensors are exactly perfect with high probability. And that gives us a little bit more control over the way information propagates in a random stabilizer tensor network than it would in a random tensor network with higher random tensors. And the fact these random stabilizer tensors are exactly perfect with high probability means we get all the error correction properties of the happy code with high probability. So you can think of this as we might construct a couple of tensor networks using this random stabilizer tensor method, and some of them won't be good toy models of ADS-CFT. We can throw those away. But with very high probability, if we keep doing this, we're going to end up with a random tensor network that is a good toy model of ADS-CFT. And again, many of the techniques from the random tensor network paper do apply to this model as well, because many of them only use second-order moments of the tensors in order to get their results. So in particular, we can still use this mapping to the Ising model for random tensors to show that the Ru-Takanagi formula is obeyed exactly for these random stabilizer tensors. And you also get that in this model, complementary recovery is exactly obeyed. So for random tensor networks with just high random tensors, you get approximate complementary recovery. And then when you have random stabilizer tensors, you get exact complementary recovery. Okay. Okay, now what about the local Hamiltonian on the boundary? What about the Hamiltonian on the boundary? How is that affected by using random stabilizer tensors? So the key property of stabilizer tensors that makes them really, really nice for this model is that they preserve the Pauli rank of operators. So if you remember, the operator that we want to map to the boundary is some local Hamiltonian term acting in the gulf. Now this local Hamiltonian term here, it's a 2 local Hamiltonian term, has some constant Pauli rank because it's only acting on a constant number of spins. And because stabilizer tensors preserve the Pauli rank, when we have this model, when we map this Hamiltonian term out to the boundary, we're still going to have that constant Pauli rank. So that means that we don't have to do exponentially many gadgets anymore in order to break this interaction down. We now just have to do a constant number of gadgets. And when you kind of push all those techniques through and look at what that means, what we find is that if we start with a holographic quantum error correcting code constructed from stabilizer tensors and then apply Hamiltonian simulation techniques to the boundary Hamiltonian, we end up with a local Hamiltonian on n polylog n qubits. So we have still had a blow up in the Hilbert space dimension. But it's much smaller blow up. And in particular, if you think about kind of wanting a constant density of spins on the boundary, then because of the way the hyperbolic metric works, you only have to go out a doubly logarithmic distance from the boundary from the actual boundary to kind of fit in all these new tensors. Okay, so if we stop and kind of take score, so we've got a toy model of ADS-CFT that has the error correcting properties we want. It's a model on the level of local Hamiltonians, and it has the entanglement properties we want for ADS-CFT. So this is kind of a nice toy model. So far, though, it's just a toy model. I mean, we've got some dynamics in here now because we've got Hamiltonians, but the dynamics is perhaps a little bit unsatisfying so far because we haven't taken into account the time dilation in the metric of ADS-CFT. Sorry, just to note, the boundary Hamiltonian has to have large interaction strengths to keep the errors small, and we'll come back to this point in a little bit. But first of all, to discuss the time dilation in ADS-CFT. So the ADS metric is given by this expression here, which I'm not going to attempt to read out.
Sorry, you covered this already, but time dynamics due to the error correction?
To the error correction. So, I mean, if you have like the perfect time dynamics without the simulation, any kind of dynamics in the bulk will just be also dual to dynamics on the boundary. So it won't kind of muck up the error correction. You'll still have this. You can kind of pause the dynamics at any time, and the error correction will still be kind of, you'll still have this sort of entanglement wedge reconstruction. When we have this approximate simulation on there, if you kind of evolve the boundary under this local Hamiltonian and the bulk under its local Hamiltonian, we will start getting slight errors in the error correction just because the simulation isn't perfect. But the errors will grow linearly in T, and basically by however small you want the error, there'll be some amount you have to make the interaction strength increase by in order to get that error at the end. Okay, so from the ADS metric, you can see, or maybe you can't see, but please believe me, time is dilated in the center of the bulk. So throughout this kind of talk, I've been saying we're just going to think about constant time slices of ADS. But, you know, the ADS metric doesn't just kind of affect space, it also affects time. So if we want to capture this in these toy models, we're going to have to sort of put this in by hand. So to do that, we're going to look at how stationary observers at different points experience time. And if you say these observers are stationary, so we set all the kind of spatial terms to 0 in here, we find that this is the kind of expression that kind of governs how stationary observers at different points experience time. So we need to kind of put this into our toy model by hand somehow. And the way we're going to do that is by just kind of translating this to the parameters of our toy model. So essentially, yeah.
Go back to the previous line. I'm a little bit confused with what you mean by time is dilated in the center of the bulk. You're in pure ADS. Every point is isometric to every other point.
So I guess these toy models we have kind of picked because we cut them off at some finite radius, we really have picked a center.
But in what sense is this an observable quantity? I mean, time dilation is something that is typically observable quantity. If every point is isometric to every other point, how is this something that can be observed?
We'll get to in a couple of slides, but we do see that when we put this time dilation by hand, there's some properties of ADS, like CFT, that we would want, that we get, that we don't get if we don't put this time dilation in by hand. So I guess it's very much a toy model, but there are some kind of desired properties that we don't get if we don't put in this time dilation. But maybe, yeah, we can also chat about it more. Okay. So when we kind of translate this to the parameters of our model, we find that we want the time at a position x, where we use x to label kind of how many layers of the tensor network we are out from the center. We find that time at a point x is given by this expression with respect to time at the boundary, where tau here is just some parameter that controls the curvature of our tessellation. So it's just some constant that depends just on which tessellation we've chosen. Okay, so what does it mean to have our time running at this speed in the center? It's not clear at all. But we're going to kind of put it in by hand just by scaling the Hamiltonian interaction strength. So when we're looking at time dynamics, the time kind of only ever appears multiplied by the Hamiltonian. So we can always just leave time as kind of something we're not going to worry about, and modify the Hamiltonian interaction strength in such a way that we kind of get this idea of time in some sense running slower in the center of the bulk. And I guess what we're really meaning is that the Hamiltonian term in the center of the bulk is weaker. So applying some Hamiltonian hit here to implement a unitary will take longer than it would applying the same Hamiltonian term on the boundary to implement a unitary, because the Hamiltonian term itself is weaker. Okay, and to explain why this kind of time dilation is something we want, we're going to have to talk briefly about butterfly velocities. So butterfly velocities here capture how fast information propagates on the boundary in the code subspace. So the idea here is that we have some information that at time P1 is kind of living on this, living in this boundary region, living in this bulk region, which lives in the entanglement wedge of A. And then when we let time evolve, after time delta t, this information is now spread to live on the slightly larger bulk region, which is captured by which is in the entanglement wedge of the boundary region A delta t. And the butterfly velocity basically is just telling us how fast is this information moving on the boundary. So given how fast information moves in the bulk, how does this, what does this map to in terms of speed on the boundary? Okay, so once we've got this kind of definition of a butterfly velocity, we can see why it's kind of desirable to modify, to kind of put this time dilation in by hand into this bulk metric. So there are a couple of things we kind of want when we're looking at boundary signaling in toy models. And the first thing is that we want that when we send a signal through the bulk or around the boundary, those two operations should take the same amount of time. So, when we send information through the bulk and we send it around the boundary, these signals should meet at the other side of the boundary at the same time. And if you think about it in a tensor network toy model, if you think about kind of each traveling along a tensor as taking like 1 unit of time, then you can see that going through the bulk, you've got a much shorter journey than you have going around the boundary. So if we had some kind of local Hamiltonian with order 1 weights on both the bulk and the boundary, then these operations aren't going to take the same amount of time. Traveling through the bulk is going to be a lot quicker. So the idea of kind of slowing down time in the bulk is that we can, these two operations now will take the same amount of time. And the second kind of reason why this Hamiltonian dilation or time dilation is nice is that it kind of gives us the behavior we expect for butterfly velocities. So if we do kind of these tensor network toy models of ADS-CFT and we allow all the bulk Hamiltonian terms to be order 1, what you end up finding is that if you look at how the butterfly velocities act on the boundary, you get that kind of information is moving far, far fast. Information, kind of when you move 1 step in the center of the bulk and look at how that is acting on the boundary, it's acting far faster than when you move 1 step closer to the boundary. Whereas when we do this kind of modifying the Hamiltonian to try and kind of capture some of the time, the way time is affected in the ADS metric, what you find is that you get these straight kind of butterfly velocities, so that it doesn't matter where you are in the bulk, the speed at which the information is propagating on the boundary is the same. Okay, so that's kind of some, yeah.
So I'm a little bit confused about how that scales the strength in terms of, I don't know what the...
Oh yeah, sorry. So x here is the distance we are from the center of the bulk. So when we're at the center, x is 0, and we have this, the interaction strength is kind of exponentially small. R here is the radius of our tensor network, and tau is just some constant that governs the curvature.
So in terms of simulation, say if you want to simulate an observable in the body by like unit time, or like a linear time, you need only logarithmic like propagation of boundary operators. Is that your way to?
Yeah, essentially, yeah. So, when something is acting deep in the bulk, don't forget it's spreading to a larger region of the boundary. So, a signal moving a small distance in the bulk and near the center of the bulk, that's equivalent to a much larger boundary distance than something moving near the boundary, moving that same distance. So, you're kind of making time run slower in the bulk, so that on the boundary, the time passing becomes equivalent. Okay, so now we've got a kind of tensor network toy model of ADS-CFT that has some of the causal properties we expect, and it has all the kind of the 3 properties I mentioned at the beginning that we want. So what can we use this for? I'm going to kind of talk briefly about one application to position-based cryptography. So first of all, just very quickly, what is position-based cryptography? In PBQC, the idea is that we're going to run a cryptographic protocol where we use the position of a prover in space-time as its credential. So the idea here is that we want to check that someone really is where they say they are. And the way we do that is by taking for 2 input points and 2 output points, we're going to send some information in towards the place where we want the honest prover to be. And we're going to ask the honest prover to apply some unitary to the information we've sent in at that point and send it out to 2 output points. And in the honest protocol, the idea is that there's just enough time for the honest prover to apply this unitary and to send the information out. And that's all the honest prover has to do, just to apply unitary and send the information back out again. But it turns out that this position-based cryptography is not unconditionally secure. So if you have enough entanglement, you can always break this type of cryptography. And the way you do that is just by applying the unitary non-locally. So you can have 2 attackers who are not at the point which we're trying to verify. They're at some points outside that point. But if they share enough pre-shared entanglement, they can always spoof the position. So they can always apply the unitary non-locally, send some information between themselves, and then send the results out to the desired output points. But there's a lot of work trying to figure out exactly what we mean by enough shared entanglement. So it's known if that the entanglement is exponential in the size of the unitary we want to apply, you can always break position-based cryptography. There is a kind of a lower bound on the amount of entanglement you need, which is linear with some constant less than 1. I don't remember the constant. But there's obviously a huge gap between these 2, what's known to be possible and what's known to be impossible. And there's kind of a lot of interest in trying to pin down exactly where the boundary is. And it turns out you can think of an attack on position-based cryptography in holography. So the idea is that in holography, you can come up with points on the boundary, kind of input and output points on the boundary, such that you can come up with a position-based cryptography protocol where in the bulk there exists a position where this unitary can be applied locally, but on the boundary there's no intersection of the light cones where you can apply this unitary locally. But because ADS-CFT is a duality, we must have that if something is possible in the bulk, it's also possible in the boundary. And that kind of implies that the boundary is doing some sort of non-local computation. And this is interesting because if you look at the amount of entanglement between the boundary regions that are kind of where this computation is being carried out, it's only linear in the input in the size of the unitary. This suggests that maybe ADS-CFT can break position-based cryptography exponentially better than known quantum information techniques. So, this is a surprising result. I think there's lots of quantum information theorists who would be very surprised if this was possible. So we decided to look at this in our toy model and see, what can we learn about either ADS-CFT or position-based cryptography by trying to do this sort of protocol in the toy model. So the way we're going to replicate this attack in the toy model is as follows. So we start out with our inputs on kind of two boundary regions at opposite sides of the toy model. And we're going to propagate this input information in just by doing swap operations. And for these operations, we don't need to do any Hamiltonian simulation in order to reason about the light cones, because these operations are kind of completely disjoint between the 2 inputs. When we get to the bulk, we're then going to apply some unitary. And this unitary is going to kind of obviously act on both these inputs together. And because this unitary is acting on both inputs together, it's no longer kind of disjoint between the different boundary regions. But using Hamiltonian simulation techniques, we can kind of come up with a local Hamiltonian that generates a unitary that applies this unitary on the boundary. And I say we can do this with Hamiltonian simulation techniques. We can always come up with Hamiltonian simulation techniques that apply this unitary, but we can't just use any Hamiltonian simulation techniques in order to reason about position-based cryptography. We really need a good simulator to keep the boundary causal. And I'll explain what I mean by that in just one slide. And then once we've done this unitary in the bulk, the idea is we then propagate out, again using these swap operations, and we get the information out on the boundary. And as long as we have a good simulator to keep the boundary causal during the second step, we can show that the boundary regions don't overlap, So in the boundary, there's no place to do this locally, therefore we must have done this non-locally. And we can also bound the amount of entanglement that was used in this protocol and show that it's linear in the size of the unitary. Okay, so this sounds great. Maybe we've broken position-based cryptography. There's just this little kind of problem of, do we have good enough simulators? And the answer is no. So.
Do we, like, is the Hamiltonian on the boundary there non-local? Or can you ensure that it's local?
Oh, we will definitely ensure that it's local.
Geometrically?
Yeah, geometrically local. So yeah, when I say a good simulator, in order to keep the boundary causal, the thing we need to worry about is this interaction strength. And in particular, in order to kind of maintain causal structure and at the same time maintain a small enough error in the simulation so that we get kind of an actual answer out to the cryptography protocol, it turns out that we need our interaction strengths to scale as some polynomial in the size of the unitary over the desired error, where we need this rate, we need these exponents to sum to something strictly less than 1. And if we could construct such a simulator, then we'd be able to break position-based cryptography using only linear entanglement. And that means that if position-based quantum cryptography could be proven to be secure by any other means, then this would imply a limitation on how good quantum simulations can actually be.
Just one question, when you say the entanglement, like what is related to the bond dimension? That must probably be pretty large, is that?
So we actually did this with perfect tensors rather than random, so we can do it. So we did it in our with just qubits. In the paper, I guess we could do it with random instead. I think we were just thought it was simpler. But yeah, I'm not sure how the.
So we have the specific subsystems to worry about.
Yeah. Yeah. But yeah, I guess the local dimension would also come in. I'm not sure exactly how. Okay, so you might be wondering, how tight is this bound? You know, okay, we've got an implication between position-based cryptography and simulation via holography, but it's only interesting if it's kind of a fairly tight bound. If it's just a very loose implication, then it's kind of maybe not massively interesting. And the truth is that for completely general Hamiltonians, this bound isn't tight. We're exponentially far away from this bound for completely general Hamiltonians. But we don't just have to apply this bound to completely general Hamiltonians. Interesting if we restrict our thinking to thinking about bulk unitaries that are generated by k local Hamiltonians for some constant k. And when we kind of plug this through the mapping, what we find is that this corresponds to a bound on simulating sparse boundary Hamiltonians. And it turns out that in this case, the bound really is, we really can get quite close to this bound. So using a different type of simulation techniques, which I won't go into, but using these kind of slightly more sophisticated techniques, we can construct simulation methods that are kind of optimized for simulating sparse Hamiltonians. And using these techniques, we can get simulators with interaction strength scaling as kind of the same expression, where now we have a plus b is greater than or equal to 1.5, where this will be exact equality for, I think, 1 sparse Hamiltonians, and then when you allow kind of, when you change this, increase the sparsity a little bit, you get just slightly bigger than 1.5. So, you know, in order to break position-based cryptography, we needed this to be less than 1, and we really are kind of frustratingly close. But it turns out that even though you get close with these techniques, when you try and use that to break position-based cryptography, it's just not useful. You end up with very large errors, even for doing kind of very trivial unitaries. So I think, you know, we can get close. This bound is kind of saying something interesting, I think. Okay, so I'll just finish up quickly with some open questions. So I guess the big one is, where's the gravity? ADS-CFT is meant to be something about the holographic principle, which is meant to be a statement about quantum gravity, but there's been no gravity in this talk at all. And I think it is interesting to ask, how far can we push these toy models before they break down? And you have to include gravity, because I think, you know, perhaps this is saying that the features of the duality you can get without gravity kind of aren't inherently gravitational. They're more of a statement about the, negative curvature of the space we're working in, and maybe we need to look at the features we can't get in order to really see where gravity comes into this duality. And kind of along those lines, there's some features these toy models are definitely missing. So there's no conformal symmetry on the boundary of our toy models. There are some other toy models that do have some conformal symmetry in the boundary, but they don't have any time dynamics. So there's a question of, can we marry these two things together? And if not, does that tell us something interesting about ADS-CFT? There's also a question about toy models that capture the full entanglement spectrum correctly. So I've said we get the kind of right entanglement scaling, and we do for the kind of von Neumann entropy. But in real ADS-CFT, we really are also interested in kind of the full spectrum of Rayleigh entropies. And the entanglement scaling we get here isn't exactly what you'd expect for that. You can kind of argue that the entanglement scaling we're getting here is what you'd expect for fixed area states in ADS-CFT. But I know that you shouldn't be able to get kind of these fixed area states for many different regions of the boundary simultaneously. So I know Chris is working on kind of tensor network toy models that have kind of a closer relationship in terms of the full entanglement spectrum to what you expect in real ADS-CFT. And finally, I think it's interesting to ask, are there other applications of these toy models? So I think in Lee J's talk tomorrow, they're going to talk about how these toy models can be used to study the Dick theory in ADS-CFT. I think it's interesting to ask about, what else can we learn about quantum information theory and ADS-CFT from these toy models. Yeah, thank you.
Say if I have a shared entanglement on the boundary, does that help not break the cryptography protocol? So what else do you need on the boundary so that you don't need such a good simulate as the ones we have are enough?
Oh, that's really interesting. No, it's not something I thought about. I'm not sure, as in if we added exponential entanglement, could we?
Yeah, or shared entanglement or something else that is supposed to help us understand how the boundary looks, right? If we believe it's something in the world.
So I guess in order to do that, we'd kind of have to, because the bulk and boundary are really just exactly dual to each other, we'd have to add additional bulk entanglement in order to get more entanglement on the boundary. And I'm not sure how that would affect the protocol because, we'd also have more entanglement in the bulk. But no, I think that's an interesting question. It's not something I've thought about. But
so if this mapping from local bulk Hamiltonians to the boundary Hamiltonians be understood as a holographic dictionary or proxy for the holographic dictionary? And if so, there are many desired properties, right, of the holographic dictionary. There are fields mapped to sources, stuff like this. Do you think there is a way to reflect that somehow?
I hope so. Yeah, it'd be great to chat about kind of what more, which properties you want and kind of how we can try and incorporate them. Yeah, not something we've thought about in detail, but I think, yeah, it's definitely interesting to look at.
This one may be the same as the first question you were asked, but do you have any hope of getting power law correlations on in a theory like this? And then I guess the hard, impossible question is back reaction? Question mark.
Yeah, I'm not sure. Sorry. No, yeah, it's not something I've thought about so far, but it would be good to chat.
Is there any sense that if I put random tensors on a random graph instead of this tessellation, or you're transitioning between different random graphs, do you think that might be?
Oh, I see what you mean. So we can look at kind of, but it's kind of difficult because obviously in the bulk you can't leave the subspace of the error correcting code because by definition you don't have those degrees of freedom. But on the boundary, if you kind of add coupling between kind of different code spaces, you really can look at, on the boundary you can look at, you can introduce dynamics where you really do leave the subspace defined by the error correcting code. And then in the bulk, obviously, that doesn't have a bulk dual if you just look at a fixed tessellation. But if you think, you can always map it to a different tessellation, which will have some tensors removed, essentially. And removing those tensors will always give you enough degrees of freedom to construct the bulk dual of the boundary map. So in that sense, if you don't start with the bulk, if you start with your boundary Hamiltonian, you can look at kind of different geometries. But it's kind of, I guess, in the boundary, what's happening is kind of it's all unitary, it's all very nice, but in the bulk, you're doing something very, very non-unitary. You kind of have to put it in by hand. So I think one interesting thing would be to look at kind of, as these random tensors with non-trivial links, can you look at a Hamiltonian that governs the boundary and also governs these kind of non-trivial links in such a way that you get this geometry kind of smoothly scaling rather than this very discrete action of just taking bulk degrees out. And that would also be nice because then you could potentially start, then you could start from either direction looking at the bulk or the boundary. Whereas at the moment, if we want to look at different geometries, we kind of have to start from the boundary.
I guess also, maybe a very naive question is one of the things that makes CFTs hard compared to normal field theories is we don't have local Lagrangians for them, right? But it seems like if I took this instead of on a random network, if I tried to use your simulation technique on Happy or Mara, I would get some explicit local thing out. Is there any sense that you expect, as I took the limit of the tensors, is there some limit in which I could actually get something which looks like a local Lagrangian for a CFT by using this technique?
I think just this technique with kind of arbitrary tensors, I'm not sure you'd ever get anything that looks conformal. I don't know why you would kind of expect to get conformal symmetry out. But I think there's papers by Dennis Steegman and Tobias Osborne where they do have kind of conformal symmetry, a kind of discrete version of conformal symmetry on the boundary. I think it would be interesting to see, but there they don't have any dynamics, they don't have any bulk degrees of freedom. It would be interesting to see if we can kind of push the techniques together somehow. And see, does the Hamiltonian get out look like what you'd expect for conformal symmetry?
So in the beginning, you mentioned that there were these overall three properties that you wanted the map to replicate. Do you need at all any constraints on the rate or distance of the air-correcting codes?
So I think in related CFT, the error correcting code really is kind of better than what you get using the happy code. I think in related CFT you can really correct for half plus, you can correct when you have half plus kind of arbitrarily small amount of the boundary. Whereas for the happy code, you kind of need 2/3 of the boundary. So I say you get the error correcting properties. The truth is it's not kind of exactly the error correcting properties. And kind of the better the error correcting code, the kind of closer you get to that kind of half plus epsilon. But in terms of the kind of getting the general thing to work without being too fussy about the constants, I think if you just have an arbitrary error correcting code kind of for each tensor that isn't this perfect tensor error correcting code, you won't necessarily get kind of the redundant encoding in the right way because the encoding isometry isn't necessarily in isometry in every direction. So you might get that kind of information from here. You should technically be able to recover it from kind of, fairly big regions which just put out something little over here, but you can also push it backwards. And if you have an error correcting code that doesn't come from perfect tensor, I'm not sure if you get that property or not. So I think you probably do need perfect tensors. Or random tensors which are kind of close to perfect.
Hi, I think I'm wondering if the first open question and the third open question are related because I saw some paper saying that more stabilizer links should be understood as graphing back reaction. Do you have any comments on that?
Yeah, I definitely think all the first three are connected. I think kind of where's the gravity is probably in one of the things we haven't managed to get yet. So yeah, I definitely think they're connected.
Sure.
And yeah, be interesting to chat about how they might be connected.